Hello everyone, my name is Salim from the University of Manchester, and in this presentation I will be describing our experiences implementing TruffleWasm, which is a WebAssembly interpreter on top of GraalVM. In this work, we describe the design and implementation of a WebAssembly guest language using Truffle Framework, which we'll see in the later slides. We look into advantages of using GraalVM and its diverse guest language support. We did this by building a standalone WebAssembly runtime and look into how we map different WebAssembly features into Truffle, and later we compare peak performance with other WebAssembly runtimes. In this work, we contributed an implementation of WebAssembly guest language using Truffle, look into how WebAssembly features map into Truffle features, and then presented a performance comparison with other runtimes. I'll start by introducing WebAssembly itself. So if you have a source code in a language such as C or Rust, this will be compiled into a single scope called a module. This module contains the code to be executed plus other components such as memory and function tables. Since the core WebAssembly specification doesn't contain features for accessing system resources such as input and output, the module will list them as imports. That is, these functions should be provided by the runtime, either implemented by the runtime itself or coming from the outside environment, such as other modules. The module can also specify which of its definitions are available outside, and these are known as exports. So for example, if you have a WebAssembly runtime, it will load a module, identify the imports required by that module, and link them to either its internal implementation or from other places such as the JavaScript runtime. One of those API that a WebAssembly runtime can implement is this one known as WASI. This is a WebAssembly system interface, a POSIX-like function calls that provide access to input and output features with capability-based access. This enforces the sandboxing environment of WebAssembly itself and can only access resources that are specified when running your program. For those runtimes that need to support WASI-based modules, they have to provide an implementation of this function call. One of the main features of WebAssembly is its linear memory. This is a contiguous memory space that can be accessed using index as its address. This memory can be defined by the module and can be exported to other modules or JavaScript code, for example. WebAssembly provides memory instruction for loading and storing different types to this linear memory. For example, this code here stores a 32-bit value 1256 into an index 4 of the linear memory. The result, when this code runs, will convert this value into bytes and store it into the linear memory. These bytes can later be read by another WebAssembly codes that load from the linear memory. This could be the same type, or could be a floating point value, or could be read by another language such as JavaScript and converted into other type. For example, JavaScript could read this and convert it into a UTF-8 string. Now, if you have a C code like this, we have a tree structure here, a tree node that has left and right. We want to see how this function count can be compiled into WebAssembly. This function passes a pointer value. Here we are working with WASM 32, where memory address are 32-bit value. To read this data, we first have to read the variable that specify. For example, here to get the left value of the tree node that was passed as parameter, we have to read, first we get the value of the first local variable, which is local 0, giving us the argument, and use it to load a value from the memory with an offset of 0. The result will be a 32-bit integer value that can be stored into another local variable, here local variable 1, and used it for comparison and so on. Also, to get the right node, we'll do the same thing, read the first argument of the function, and then get the value with offset 4, since the first value will occupy 4 bytes. WebAssembly code itself is organized into blocks. This block can also be nested inside each other. To branch to the outer blocks, WebAssembly provide branch instructions such as the one here, br_if. For example, if conditional branch jump to the, for example, this conditional branch here we have jump to its nearest block, hence the value 0. If a target is a loop, if the target of a branch is a loop, the execution flow goes to the beginning of the loop. So if we are branching to the loop, it will go to the beginning of the loop. And if we are jumping to a regular block, then it will go to the end of the block. Now, so this is WebAssembly in a nutshell. Now let's look into Truffle Framework. Truffle Framework itself is a framework that helps us build AST interpreter on top of the Java Virtual Machine. AST interpreter, the abstract syntax tree that we have. We do this by converting the guest language instruction that we have, for example here WebAssembly, into truffle nodes, which can be annotated with additional information such as profiling information, assumptions, and other detail that can be used for partial evaluation by the Graal compiler to generate optimized code. This node can be designed to be specialized based on the runtime information such as type information, and can be useful, for example, to separate between fast path and slow path implementations. This specialization can be guarded with checks, and together with caching mechanisms that are available in Truffle can be used to generate optimized specialized code. Now let's look into our implementation of TruffleWasm. Let's say you have the source code and you have a compiler that can generate WebAssembly, such as the Rust compiler or Clang compiler. This will produce a WebAssembly module. We load this module into TruffleWasm and generate Truffle AST from its instruction. That means we convert each instruction or each WebAssembly instruction into a Truffle node and build the AST for each function. Then the AST interpreter executes this and collects profiling information. Later, hot code will be compiled by the GraalJIT compiler. We also provide implementation for imports, functions that can be called such as the WASI API, and we also provide a proxy implementation to call to other Truffle language such as JavaScript implementation that's available on top of GraalVM. So we can generate an AST and see from WebAssembly instruction, build the abstract syntax tree, and we also provide branching control flow using control flow exception. This is an example. For example, if we have a conditional branch, br_if here, the child node of that branch will be the value that is read from the stack here, t local, as you can see here presented in a tree form. When this branch is taken, we throw a control flow exception at runtime, which can later be caught by the outside block or further outside blocks. For the linear memory, we use the Java unsafe API to implement the linear memory itself and its instruction. Here we allocate memory using the Java unsafe API during initialization into the number of initial pages specified by the module. This memory can be grown at runtime using a memory.grow instruction. The module can specify the maximum page the memory is allowed to grow to. For WebAssembly 32, there is also a hard limit, which is a 4 GB, and of course the actual memory available on the system. In each memory instruction, we bound check the address to ensure that it is accessing the space within the linear memory provided. So for example, if we have this load instruction here, a value at address 4 and an offset 0, what we'll have to do here, first we'll have to get the value 4 here, and then we have to calculate the effective address. An effective address is the address itself plus the offset that we want to read the value from. Then we'll have to check that this effective address plus whatever byte the load instruction want to get is inside the boundary of the linear memory. Because we are using the Java unsafe API, we also have to convert this effective address later into the native address that can then be used to read the value from the memory. This will be repeated each time this code executes. And we can reduce this if we can profile and ensure that the value we are reading does not change. Then we can reduce. We only have to do this calculation to calculate the native address first, only once. We do this using Truffle's assumption and caching mechanism. In the first time, when a memory instruction runs, we calculate the effective address and the native address and cache this with a specialization which will be used in all subsequent execution of this instruction, guarding for the address value being the same, that ensure that the value does not change. We will also need to make sure that if the memory grows happen, which means now the linear memory might have moved from the initial native memory it was stored. This code is discarded and the value are recalculated again. Since memory reallocation will generate different spaces for the linear memory, to make sure there is no much overhead for this, that every time you discard the machine code, it doesn't cause overhead. We have tested this. So we have taken the binary tree program from a shootout benchmark which perform many memory growth throughout the execution. We're experimenting with this by changing the initial memory size. So by default, Clang, for example, initialized the page size to 2 at the beginning of the program, and this can then be grown multiple times. We compare this with the execution time. We execute this program 100 times, and we measure the time it takes at the beginning, the first iteration after it has stabilized, and the time it takes at the end of the iteration, while also changing how many initial page size we provide. As you can see from the green lines here, there is no much overhead associated with the load and store operation that we have. For the peak performance, we compare with WASM Time, which is a standalone implementation developed by Bytecode Alliance. For the shootout benchmark, we are achieving near WASM time speed in most benchmarks, and here we have a geomean overhead of 4% compared to WASM Time. And for Polybench C, which was used in the initial WebAssembly paper, we also achieved near WASM time speed for most benchmark with 4% faster geomean. We also implemented interoperating with the GraalJS. GraalJS is an implementation of JavaScript on top of GraalVM. We did this by adding support to WebAssembly JavaScript API, which provides JavaScript with built-in support to instantiate a WebAssembly module, provides it with the required import, and then access its export. We use proxy executable to call the imported function and make call back to the JavaScript. This work is currently in the initial state for the interoperability part, and we compare with Node.js, where TruffleWasm is 55% slower compared to Node.js. We are working on improving the performance and interoperating with other languages. In conclusion, we have presented an implementation of a standalone WebAssembly runtime that can run standalone modules and interoperate with other Truffle languages such as JavaScript. We compare peak performance with TruffleWasm and WASM time. We are also working into comparing with other runtimes such as Node.js. And here we have provided a platform for investigating WebAssembly itself, its core features, how we can improve the performance of it, and how it interoperate with other languages. Thank you very much.